Good morning, children. Today we are going to start chapter 3, Atoms and Molecules. Let's go for introduction. Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher, Maharshi Kannad, you can underline this, postulated that if we go on dividing matter, padarth, that is Hindi word, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakuda Katya Yama, elaborated this doctrine and said that these particles normally exist in a combined form. They don't exist in the single. They exist in the combined form, which gives us various forms of matter. Around the same era, ancient Greek philosophers Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these indivisible particles atom, meaning indivisible. All this was based on philosophical consideration and not much experimental work to validate these ideas could be done till the 18th century. By the end of 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antoine Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. And in your reduced course, this topic is excluded. 3.1 Two laws are there. Laws of chemical combination. In that, two laws are there. One is law of conservation of mass. Law of conservation of mass means weight. As we have chemical reactions in this reactant and products, so we have LHS and RHS. Okay, I'm giving you just idea of that. LHS and RHS. So they are saying that the mass of an element or a compound before the reaction and after the reaction will remain same. So they are explaining this with the activity. But we don't have to go through this. Second one, law of constant proportion. Proportion of the element remains same. And these are the postulates for Dalton's atomic theory. According to Dalton's atomic theory, what are the characteristics of atom? So that and all is given. So let's read that at least. All atoms is made of very tiny particles. All matter is made up of very tiny particles called atoms, which participate in the chemical reaction. Atoms are indivisible particles which cannot be created or destroyed in a chemical combination, or we say chemical reaction. Atoms of a given element are identical in mass and chemical property. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. The relative number and kind of atoms are constant in a given compound. Okay, so that was just a highlight of Dalton's atomic theory. And the next topic, that is your learning first topic, what is an atom? This is a beautiful picture of atom. Here you can see in the middle something is there, and also orbits are, you are able to see orbits, and in the orbit also something is moving. What is an atom? From the picture we can make out there are particles. Okay, these particles are proton, electrons and neutrons. These three particles make the atom. And where are they? Proton and neutron are in the nucleus, that is in the middle part of the atom, and electron is revolving around the nucleus. That means they are moving particles, and protons and neutrons are steady, they are stationary. Now what is atom? The atom, the smallest unit of matter that gives a substance its chemical properties. Now in middle of the atom you have nucleus, neutron. In that, what are the charges? No charge, but some mass as a proton. Electron is moving around, negatively charged, and proton is positively charged. This one is according to Bohr's atomic model. Here you are able to see in the middle plus, that is proton, and one more particle you are able to see, that is neutron. Okay, positive charge, and negative charge you are able to see the dot dot or tailed type structure. This tailed type structure shows that they are in the motion. They show the motion of an electron. The Bohr's model of an atom showing electron in the orbit around the nucleus, which consists of protons and neutrons, and the tails on the electron indicate motion. They are only the moving because they are light in weight compared to the proton and neutron. And the weight of the atom also, because of also due to only and only proton and neutron. Very less weight electron has. One of the example of helium atom, you can have helium, the number of helium, first one is hydrogen and second is helium. Okay, that means the atomic number of helium is 2, and whatever is the atomic number, that means they have proton and electron. Okay, same number of proton now here, and moreover they have same number of neutron. Sometimes only neutrons are changed, and that will give rise to isotopes. So that is the next case of this. So here you can see in middle you have 2 proton, 2 neutrons, and outside on the orbit you can see 2 electrons. And why they have written 4? Because this 4 shows the atomic mass of the helium. Okay, so and it has only one orbit. Regarding this we will study later on. Let us continue here. Have you ever observed a mason building walls? From these walls a room and then collection of rooms to form a building. What is a building block of the huge building? As we have cell as our functional unit, is it? Many cells make the body. So similarly, many atoms make the matter. What about the building block of an ant hill? It is a small grain of sand, the smallest part, the smallest unit on which the big things are supported or made. Similarly, the building blocks of all matter are atoms. How big are atoms? Very small. But we have to know the size of the atom. They are the smallest thing in the world. Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms, when stacked, would make a layer barely as thick as thin sheet of paper. Atomic radius is measured in nanometers. Nano 10 raised to 9 meters. The 1 nanometer, here they are telling 1 by 10 raised to 9. So we can say 10 raised to minus 9. Okay, is equal to 1 nanometer. Therefore 1 meter is equal to 10 raised to 9 nanometer. Relative sizes of atoms. Radii. These are radii in meters. Example, atom of hydrogen 10 raised to minus 10. Molecule of water 10 raised to minus 9. बड़ा होता जाएगा, धीरे धीरे वो बढ़ता जाएगा. Okay, उसका radius and we can see. See atoms of hydrogen we cannot see. Molecule of water we can see. But means if we go inside we can draw the structure. But that also we can't see. Molecule of hemoglobin, if you go for this more and more, then through electron microscope you can see it works like, because they are cell and they are very small. Under microscope only we can see. Molecule of hemoglobin 10 raised to minus 8. Grain of sand, this we can see 10 raised to minus 4. Ant we can see 10 raised to minus 3, and apple 10 raised to minus 1 according to the relative size in radii. We might think that if atoms are so insignificant in size, मतलब बहुत छोटे हैं, then why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there. हम उसको देख नहीं सकते, but everything which you can see with your eyes, which you can feel, is made up of matter, is made up of atom, and that and all matter is made up of atom. We may not be able to see them, but they are there and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces of elements showing atoms. पहले ज़्यादा कुछ दिखता नहीं था, but technology is improved a lot, and now we can see at least some layers of elements. Otherwise, it was very difficult to see. And here one example they have given, an image of the surface of silicon. You know where silicon and germanium are used. They are semiconductors and they are used in the microchips and all. Now the world is of silicon and germanium. This they have shown. Okay, an image of surface of silicon. One more I show you. See, this is a beautiful image of surface of silicon, zigzag, zigzag, zigzag. Okay, and when we draw, then also the shape of silicon is coming like this way, and this way actually the ring type structure is the ring type. Okay, they have seen this all, and then afterwards they have drawn. So this is surface of silicon, and the formula for it S8. Atomic symbol is S, but if we go for the molecular formula, which is the next topic, that is okay, molecule is the next topic. Here molecular formula is S8, and they are combined with the chain type structure, and this is a okay. So this way structure you can see in the silicon if you go for more and more high power microscope. Next topic, what are the modern day symbol of atoms of different elements? Modern day is different. It is not that the first scientist has given the things which are present today. No, many scientists have gone through these things and then it is improved year by year, and then now what are we studying is the result of contribution and hard work of all the scientists who has given their life in finding out these all symbols. Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element. That is, one atom of that element. Berzelius, सबसे पहले इन्होंने दिया underline, suggested that the symbols of elements be made from one or two letters of the name of the element. जो भी element उनको मिल रहा था उसके नाम कैसे दिए जाएंगे, तो उन्होंने कुछ सिंबल डाले. ठीक है, ये ओल्ड सिंबल है. राइट नाउ वी आर नॉट यूजिंग दिस. These are the old symbols. Symbol for some elements are proposed by Dalton. More, I will show you picture. Hydrogen. Today, at least you know 1 to 20. Okay, you know hydrogen is denoted by only H. Carbon only C. Oxygen only O. But they make these symbols as a simple. Before that it was little bit difficult, and they gave the design like this way, hydrogen, this design, and sometimes they are asking for 1 mark also. So children, this you have to remember, symbol you have to remember. This car जैसा कोई कंपनी का सिंबल है, फॉस्फरस है. सर्कल एंड सी कॉपर, गोल्ड, कार्बन सल्फर प्लस वाला, लीड लेड, P platina, oxygen, iron, silver, mercury. See, gold and mercury, what is the difference? Okay, so when it comes in the exam, so you don't think that both are same. So at least to go through some symbols for some elements, at least how much which is given in your book. Okay, more I'll show you. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name of copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from the English word meaning yellow. And nowadays, IUPAC, underline definition, International Union of Pure and Applied Chemistry, ये जो है वो एलिमेंट्स के नाम देता है. Is an international scientific organization which approves names of elements, symbols and units. Many of the symbols are the first one or two letter of the element's name in English. The first letter of symbol is always written capital, that is uppercase, and the second letter as a small letter. This now we are using hydrogen capital H, aluminium AL and not A and capital L. से कि ये चीज़ ध्यान रखना, फर्स्ट वाला ही कैपिटल है, दूसरा कैपिटल कभी नहीं. Cobalt we are going for C and small o, capital C and small o and not both capital. Both capital it will be carbon monoxide, so this will be wrong. Symbols of some elements are formed from the first letter of the name and a letter appearing later in the name. Examples: chlorine, so C capital, L small. Zinc, Z capital, N small. Other symbols have been taken from the names of elements in Latin, German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum. Sodium is an A from Latin name natrium. Potassium is K from Latin name kalium. Therefore, each element has a name and a unique chemical symbol. Okay. Now, about this I show you the picture of Dalton. This one. This is a picture of John Dalton and 36 chemical symbols he has created in 1803. Okay. These are the chart. Oxygen, hydrogen, nitrogen, carbon. Okay. And these are the elements. So some elements you can go through. Hydrogen, azote means nitrogen, carbon, oxygen, phosphorus, sulfur, magnesia. Names are also little different compared to today's. Okay. Here strontium, barium, iron, zinc, copper, lead, silver, gold. This we have done. With the color also. Just now we have read that on the base of color yellow they have given this. Okay. Name symbol for gold. Aluminium, calcium. See, colors are there. Okay, so today I stop here, then I will continue in next class.